A board game with color squares. You're on yellow. Roll the dice. Land on blue. Roll again. Land on red. Your next move depends only on where you are right now, not on the sequence of squares you visited before. This is the Markov property. The future is independent of the past given the present. Simple, powerful, and it runs the most important sampling algorithm in modern statistics. The Markov property means memoryless. The probability of moving to the next state depends only on the current state, not the history. Tomorrow's weather depends on today, sunny, cloudy or rainy, but not on last Tuesday. A molecule's next conformation depends on its current shape, not its folding history. This simplification, forgetting the past, makes the math tractable. Without it, you'd need to track every possible history, an exponentially growing problem. The transition matrix encodes all the move probabilities. Rows are current states. Columns are next states. Each entry Pij is the probability of moving from state I to state j. Each row sums to 1. You must go somewhere. A 3-state weather model from sunny 70% chance of staying sunny, 20% cloudy, 10% rainy. From cloudy 40% sunny, 30% cloudy, 30% rainy. The entire dynamics of the system live in this single matrix. Where will you be in 2 steps? Multiply the transition matrix by itself. P squared gives the 2-step transition probabilities. P cubed gives 3-step. P to the n gives in-step probabilities. As n grows, something remarkable happens. The rows of P to the n start to look identical. Regardless of where you started, the probabilities converge to the same values. The chain forgets its starting position. The stationary distribution, pi, is a vector that satisfies pi times p equals pi. Apply the transition matrix, and the distribution doesn't change. After enough steps, the fraction of time spent on each square converges to pi. Start on yellow, eventually 30% of your time on yellow, 45% on blue, 25% on red. Start on red, same long-run fractions. The stationary distribution is the equilibrium, the resting state of the chain. Not every chain converges. 2 conditions are needed. Irreducibility. You can reach any state from any other state, no isolated squares. Aperiodicity. The chain doesn't cycle with a fixed period. You're not forced to alternate between 2 states. If both conditions hold, the chain is ergodic. It has a unique stationary distribution and converges to it from any starting point. Ergodicity is why MCMA works. The Markov chain forgets its arbitrary starting position and settles into the target posterior distribution. The Markov property memoryless. The transition matrix, all dynamics in one grid. Multi-step transitions, matrix powers. The stationary distribution, the long-run equilibrium. Ergodicity, the guarantee of convergence. Next, why this board game runs Bayesian statistics and self-fate prediction.